Hello, Professor Başar. Hey, can you hear me? Surely. I can't hear you.
That's right, because
Oh, yeah,
I was
now
mute.
I can hear you. Now I can hear you.
Now you should be able to hear me.
Yeah. Great. Yeah, very clear. Yeah. So my name is Ethan. So others will join soon. Yeah.
Okay, how many are you expecting normally? How
So
many
not
do you have?
in total in different platform, about say 200.
Okay.
Yeah.
That has been the average over the last few seminars.
Yeah. Not only Zoom. So in total, yeah. Jordan and Zhaoran are here.
Yeah. Hi, Professor
Hi,
Başar.
Zoran.
Hi. How are you doing?
Hi, how are you?
Oh, good. How are
Hi,
you
Professor
doing?
Başar. How are you?
Good. How is research going?
It's going steadily, but slow,
Yeah.
but it's going.
Yeah.
So, are you in Champaign?
Yes. And it's difficult to travel, actually. I do all my sort of business, in fact, from home, not even from office.
Mm-hmm.
I'm at home right now also. We have quite a good system here. We just started the semester on Monday.
Oh.
And most of the courses are offered online.
Yeah.
And we have faculty and students who have to enter the buildings as well as staff. They have to get tested twice a week.
Mm-hmm.
And
same
without
here.
the test results, they cannot enter buildings.
Great.
How is it there?
It's the same here. I just had my saliva test this morning, and we also need to have the test twice a week. But,
so you do have saliva, not the nasal swab?
No, it's using saliva.
Okay.
So you need to spit the saliva into a tube and sufficiently amount of saliva. It's a lot. Yeah, it's a lot.
And do you have to do it once a week or
twice a week?
Twice a week. Okay,
yes.
the same as here.
Yeah. Yes.
Yeah.
Yes, but it's mandatory for those graduate students who go to the buildings regularly, say 8 hours per week. But if you are doing, I mean, for those doing theoretical research, my students, for example, they don't go to the building at all, and we do all our interactions through Zoom. Yeah. I also plan not to do this future saliva test. Today I do it just to see how it works.
Okay. Do you have how do you get the results? Do they email them to you, or is it? Do you have an app? We have an app here. It shows up on the app.
Yeah, we also have the app. It's part of the Princeton mobile app. They have a new function, new feature for the COVID testing kit.
So was it developed there on campus, the app?
Yes. For developing the app, I don't know, but we have to test on campus.
Here, my colleagues say that they have developed the app actually for that purpose.
Okay.
And the saliva-based test was also developed here, as well as at Yale, but the Yale followed us.
Mm-hmm.
Yeah.
Yeah, Kachin also told me that you are doing research on epidemic control.
That's right. Yes.
That's awesome.
Yes, both the analysis and modeling, and there are also interesting. These are all nonlinear models, and there are interesting control stability problems there, and everything is very sort of an intuitive, but the real challenge is model identifying the parameters of the model, use data. So it has to be a data-driven modeling.
So the model is you are talking about is an epidemic model like SIR.
SIR and SIR is the basic one, but then there is between the S susceptible and the infected, there is an asymptomatic phase where you do not show any symptoms, but you can infect others.
Yeah.
And so there are these more models. So these are called SAIR. And the other thing is also SIR assumes that after you are recovered, you are immune from it. And that may not be the case. And we have several examples of that. And in different countries, they are reporting that those who had the virus and then who had recovered fully, they have developed it again. They
yes. So, yesterday I saw a piece of news.
So you can become susceptible again, at least a certain percentage after a certain period of time after R. So it's not only SIR, but maybe SAIS. Some part will be susceptible.
I see.
And these are all Markov chain models, and in the limit, the mean field limit lead to differential equations, nonlinear differential equations.
I see.
Yeah.
I see.
So should I try share my screen?
Yes. Yes.
Yeah.
Yes.
That'd be great.
Yeah, that'll be great.
How does it look?
Can you try full screen?
This is full screen.
Oh, it seems frozen.
Yeah, there's a block.
Yeah, seems frozen.
On the right corner.
Oh, there is something on the.
Yeah, it seems your screen is frozen, seen from our screens.
Oh,
Yeah.
I see. So.
Can you redo it?
Sharing is paused. Bring your shared window to the front. Okay, and then let me do that. I can bring it to the front. Let me. Interesting. This is happening the first time to me that it's not.
Now it's unfrozen.
Now it's unfrozen, but you don't see. I'm not in the full.
Yeah, not in the full screen yet.
Not in the full screen. So let me see whether now to go to the full screen, I have to go to view and then the full screen mode. Let's see what it will do. Did I lose you?
No,
yes.
but
I think
it's not full screen yet.
Yeah, it's.
I mean, I do full screen on my laptop, so interestingly that it doesn't.
Yeah, this
So,
goes to the next page, but it's not full screen.
Yeah.
Yeah, no, I know it's not full screen now, but when I do full screen on my laptop, I go under view and then do full screen mode. That's not what I should do.
Since you are using Apple, can you try preview? Yeah, we see that Adobe usually causes some problem in share screen.
Yeah, maybe you can try the preview app.
Yeah, open the PDF as a by preview.
Okay. Let me go to preview. Okay, so
you are still sharing the Adobe. Can you?
yeah, I have to stop sharing that.
Yeah.
Okay, and now share screen, and let me see. Okay. So now do I, in preview, I go I go to full screen?
Yeah.
Mm-hmm.
Yeah, perfect.
Yeah.
Can you move the slides a little bit just to make sure everything works?
Yeah.
Well, this should be.
I think you need to use the left, right in keyboard. Yeah.
Yeah, it works.
Yeah. Yes. We can also see our mouse, so you can illustrate things using.
Okay, you can see the mouse.
Yeah. Yes.
Okay.
Yes.
Okay.
Yeah.
Good.
So,
I didn't know that. I have been using Adobe, but I did not run into that problem before. Interesting.
Yeah.
yeah. So we are going to begin at about 3:02, and
okay, sure.
So we will try not to interrupt you during the talk, and
Okay.
we will gather the questions raised in the Q&A function
sure.
after and collect them after and send them to you after the talk. So there will be a Q&A section after the talk, which, depending on the number of questions, usually lasts for 10 minutes.
Okay, sure. And people can send me after the talk by email also any questions that they may have.
Thank you. That's very nice of you. Thank you. Yeah, I see Kai-Ching is here.
Yes, yes. And several of my students will also be there.
Yeah, yes. See many familiar names.
Do we want to have Bing and Kai-Ching into the panel, and then they can probably answer questions?
Oh yeah, yes.
Do you know how to do that?
Why not? Because I'll essentially be presenting the work with them, and there's an archive paper which I'm going to also announce here.
Should I do it?
Yeah. I think Bing is also in the audience, but
sure.
yeah, I don't know what to click.
So they can also participate in the answer question answer.
Right?
Yeah, Kai-Ching is here.
Bing Hu, right?
Yeah. The third one.
Oh, hey, everyone.
Hi, Kai-Ching.
Hi, this is Kai-Ching.
Hi, Kai-Ching.
Hey, hi, everyone.
So we will start in 1 minute.
Sure.
Yeah, Jordan, let's start.
Okay. Hi, everyone. Welcome to the online seminar on mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my great pleasure to introduce our distinguished speaker, Professor Tamer Başar from UIUC. Professor Başar is the director of the Center for Advanced Study, Swanlund Endowed Chair and Center for Advanced Study professor in the Department of Electrical and Computer Engineering. He has also served as the interim dean of engineering and interim director of the Beckman Institute for Advanced Science and Technology at UIUC. Professor Başar is a member of the National Academy of Engineering, fellow of IEEE, AFAC, and SIAM, a past president of the IEEE Control Systems Society, CSS, the founding president of the International Society of Dynamic Games, ISDG, and a past president of the American Automatic Control Council, AACC. He has made fundamental contributions in control theory and related fields such as game theory, network analysis, and multi-agent systems. His research has shaped the control theory we are using today. He has received numerous awards, including the highest awards of the IEEE CSS, AFAC, AACC, and ISDG, the IEEE Control Systems Technical Field Award, and a number of international honorary doctorates and professorships, most recently an honorary doctorship from KTH Sweden. He has over 900 publications in control, systems, communication, optimization, networks, and dynamic games, including books on non-cooperative dynamic game theory, robust control, network security, wireless and communication networks, and stochastic networks. The title of Professor Başar's talk is Policy Optimization for Linear Optimal Control with Guarantee of Robustness. Please join me in welcoming him.
Thank you. Thank you. And hi to everyone. And where you are. And here at Illinois, it's afternoon. So I'm assuming most of you are in the United States and are also in similar time zones. So this is based on a recent work, fairly recent, joint work with my PhD student Kai-Ching Zhang and also my colleague at Illinois, Bin Hu, my faculty colleague. And there is an archive paper which discusses in detail what I will be talking about here, as well as including all the proofs and so on. So I'll mention that as we go along. So the outline of the talk is as follows. I'll provide a brief introduction to reinforcement learning and policy optimization, and then delve into policy optimization methods for controller design, and then bring in robustness, and that's the main theme of this presentation. And there are different ways of approaching robustness, and there are essentially 3 main frameworks that I'll be introducing. and talk about the relationship between those three frameworks. Then this will lead to what we call a mixed design problem, which is H2 optimization subject to H infinity, which is a robustness criterion bound. And that is a unifying framework which actually covers all three frameworks that I'll be introducing. And one of these is the risk-sensitive controller design, and then I'll spend a little bit more time on that one. And the difficulties in developing policy optimization methods for these types of problems is that, first of all, it's a non-convex optimization problem. And there is also lack of coercivity, and which means that essentially when you go in the direction of the gradient descent, it could take you outside the constraint region. And so we will be introducing the notion of implicit regularization, which some of the algorithms that we have developed actually satisfy. And under this, then it's possible to develop a theory of global convergence for two of these methods, policy optimization methods, for linear control problems. And they have sublinear rates, convergence rate, and locally they feature superlinear rates. And then I'll be talking about very briefly on extensions and conclusions. If I have time in between, I'll present some simulation results. Now, the reinforcement learning has, as we all know, achieved tremendous success in sequential decision-making problems as well as in continuous control tasks. And some examples well known to this community are game of Go, video games, and robotics. And most of these hinge on an algorithmic framework which is provided by policy optimization. So this involves function approximation and the ability to handle large continuous spaces. Policy optimization is quite easy to implement and is scalable to high dimensional control systems. And it also enables data-driven sample-based search. Some prominent examples of this policy optimization is reinforced, active critic algorithms, natural policy gradient, which I'll be talking about, deterministic policy gradient, the trust region, policy optimization, and proximal policy optimization, just to list a few. So let me first give a brief sort of an introduction to policy optimization for optimal control, and then I'll bring in robustness. So what's a standard optimal control problem? We want to minimize, and this is I'm formulating this in discrete time. It's possible to formulate it in continuous time as well, but in this talk, I'll be talking mostly on discrete time control problems. You minimize an infinite horizon cost, C of x t ut, and summed over the infinite horizon from t equal to 0 to infinity. And then there is the state evolution of the state equation, which is given here as xt plus 1 equals to f of xt ut. And generally there is a constraint set for control ut, and sometimes there could in fact even be constraints on the state itself, like we don't want the state to leave a certain predefined region. Now, the policy optimization approach to such optimal control problems is you parameterize the control policy. So the control policy, this is a feedback policy, which the control at time t depends on the state at time t. through a mapping, and I'm assuming that we have a time invariant mapping in this case, which is most of those infinite horizon time invariant problems display. And so you parameterize the mapping mu. So I denote this by mu of theta. And then you optimize with respect to this parameter vector theta. And perhaps the simplest case is the linear quadratic regulator problem, which has been extensively used in applications in various domains, all the way from engineering to economics. Here the f is linear and c is quadratic. And the constraints that there is no constraint on the control, it's an element of some m-dimensional, finite dimensional Euclidean space. Now, in this case, the parameterization for linear quadratic regulator problem, one can show that under certain conditions, you have a linear control, linear feedback control, which is optimal. So therefore, the mu theta x we can write as minus kx, where now k is a matrix, which is the parameter theta is essentially the elements of k, and you want to be minimizing with respect to k. Now, the downside of the linear quadratic regulator formulation is that it's not robust to noise, which may enter into the system. And it's not robust to disturbances. And it's not robust to modeling imprecisions. And so to remove these disadvantages or these cons, the robust optimal control theory has been developed, has been proposed and developed, where you optimize a certain objective functional and along with some guarantees of robustness. And so that the solution will not be that sensitive, optimal solution to any imprecisions that you may have in the modeling. There are different ways of modeling robustness. One is risk-sensitive control, which I'm going to discuss. The other one is using an H-infinity norm constraint, where H-infinity is a robustness sort of a measure, and that theory has been developed for that kind of framework. And then the other one is the worst case disturbance. That is, all the unknowns you can model as being controlled by an adversary. And that leads to a zero-sum game. The controller is the minimizer, and the adversary is the maximizer, which the maximization is under some constraints. So as I indicated in the outline, the H2 H-infinity mixed design that I'm going to talk about is unifies these three, and particularly I'll talk about the connection to risk-sensitive control and H-infinity norm constraint. And so this mixed design, what H2 H-infinity means is that you minimize an H2 norm and subject to an H-infinity norm constraint. And I'll be discussing this in the linear context, that is for linear systems, that is the parallel of the LQR systems. Now, it's well known that this is a non-convex optimization problem. And that's one of the difficulties that comes in. And then there's also the non-coercivity, which I'm going to talk about. So the reinforcement learning and many optimal control problems, many decision-making problems can generally be written in the following form. You are minimizing a certain cost function Now, normally in reinforcement learning, one talks about reward functions, and you maximize rewards, but we can easily make the analogy here to that, and then we are actually cost minimizer in this framework rather than reward maximizer. But the theory to be developed definitely applies to reward maximization as well. So so you want to minimize over some parameters k, and which belongs to some set script k. So the k itself is a parameterized policy. That's the controller, as I had on the previous slide. And the objective is to minimize j. And then you want to make sure that the constraint set k is that the solution stays in the constraint set throughout this process, throughout the optimization process and the learning process. And this constraint set is an important one, but it's sometimes implicit. And for example, in the linear quadratic regulator problem in discrete time, so this is the state equation, the linear, what I had earlier. And then you want to minimize a quadratic cost function. But the condition on k is that k has to be stabilizing. So what that means is that the spectral radius of a minus bk, after you substitute for u minus kx, then the closed loop system has the matrix a minus bk, and you want the spectral radius of this to be less than 1. And this is a non-convex constraint set. Okay, so in this case, it's kind of implicit. This is without that, assuming that you have controllability and observability, you cannot have a finite cost. So it's a very natural condition to impose. And there are other examples of k, such as the boundedness of k's norm, for example. You can place some constraints, norm constraints on k, or some safety constraints on the states. Now, the robustness constraint on k. So in the LQR problem, the main constraint on k is that it leads to it should lead to a stable closed loop system. But when we bring in robustness, then this is something beyond stability, and it's something that's of paramount importance. So what do we mean by that robustness? So here you have a plan. You can take this as a linear plan. And you are developing here, I have a measurement feedback, but you can take y to be the state as well. So then it will be a state feedback. And so that's how control is generated, input. But we are allowing some perturbation around the plant. And this is known as a delta perturbation. And what we are interested in is the quantity, which is the transfer function from W to the output Z. And so this G delta model covers many robustness considerations. For example, if you have in the original plant, if you don't know the matrices A and B, and you can allow some perturbations around these matrices, and you want your controller, the controller that you pick, to be robust to these perturbations. You can have time varying parameters, A and B, and this would also cover that. And even dynamical uncertainties you could have, like an unknown model order. That's also covered by this. So the H infinity norm, so how do we capture that robustness? Of course, you cannot allow an arbitrary delta there. And so there is the small gain theorem that tells us sort of what the relationship should be between delta and maintaining a robustness margin. And the small gain theorem tells us that the H infinity norm of this transfer function, if you want it to be less than a certain amount gamma, then, if you pick the delta to be, this is in the discrete time from L2 to L2, to be less than 1 over gamma, so that's the choice that you are allowing for perturbations which satisfy that inequality, that then the G delta is input-output stable. So you can maintain input-output stability in the face of perturbations which satisfy this inequality, as long as your H infinity norm of the transfer function is less than gamma. And note that this, of course, does not depend on the delta itself. So, to maintain robustness, we actually, in addition to this spectral radius condition, which is the stability condition, we also require that the H infinity norm of Tk be less than gamma. And so that leads to a certain level of strong, robust stability. So this brings a new element into the constraints set. Now note that as gamma goes to infinity, so which means you are relaxing this, so you are allowing the H infinity norm to be any value, then this is the same as the LQR. All it boils down to is the stability region of LQR. So whatever we obtain for this type of a constraint is a special case if we pick gamma sufficiently large, should also yield the results for LQR. So the open questions here is how can we enforce or maintain robust stability in policy optimization, RL methods, during the learning process? In other words, you want to make sure that K itself always stays within the constraint set, does not leave the constraint set. And the second question is what are the global convergence guarantees, if any, and rates of convergence of policy optimization methods in learning for robust control, again, in the context of this linear controller design. Okay, so let's go into some specifics. The kind of systems under consideration are linear systems, but note that as compared with the LQR problem, there's an additional input, and this essentially models the perturbations around the system, nominal system. And then Z is the controlled output. So you want to minimize the norm of Z over an infinite interval. And then you have the discrete time version of this is similar. So I should, this is a good point to bring to your attention this paper. And I mentioned this at the beginning of my talk with Kai-Ching, Bin, and myself. It's an archive, and it's a 65+ page preprint, and it has all the details. Here I'm going to talk only about discrete time. That paper also has the continuous time results, as well as full proofs of the convergence and rates and so on. So for this problem, the Tk is given in this form, assuming that U is equal to minus Kx. In other words, you use linear feedback laws. And then this essentially says that when you take the norm of Z, the Euclidean norm of Z, there's no cross terms between X and U. If there's any cross term between X and U, that can easily be handled by proper redefinition of some of these terms. But here the assumption is that the E transpose C is actually equal to 0. And the E transpose E is R, where R is generally taken to be positive definite. It means that you have a positive cost on U. So the transfer function in the case of the continuous time system is given by this, and for the discrete time system is given by this. This is quite standard. So what's the H infinity norm? For the continuous time, it's from L2 to L2. You have essentially the singular value of the transfer function on the imaginary axis. You look at the maximum of this. So that's the H infinity norm. And for the discrete time, the H transpose H, and you look at the maximum eigenvalue of the symmetric matrix and non-negative definite matrix, and it's a square root of that, and you take the supremum over all theta. So this is the H infinity norm, and here, as I indicated, I'll be focusing on the discrete time setting from now on. So the mixed H2 H infinity control synthesis is, this is the problem that we want to solve. Now I want to discuss some equivalent representations of J of K, the objective function in this case. And there are the J upper bounds the H2 norm, and for this mixed H2 H infinity control synthesis problem. And it has different forms. One can express it in different forms. These are all equivalent. This one does not explicitly involve the gamma, this bound here, and the PKDD transpose. And then the P sub K satisfies, is given as the solution of a Riccati equation. And then the same PK is used here, but this one depends on gamma. And we're going to use this actually in our formulation. I'll show that this is also the risk-sensitive control problem also leads to this JK. But the two are equivalent. And so this is an optimal control with robustness considerations. Okay, so this covers, as I indicated, risk-sensitive control problem. The risk-sensitive control problem is one where you have a stochastic system, again, linear system, but driven by a noise sequence. This is IID noise. Initial state is Gaussian with zero mean and variance, covariance x0. And WT is this stationary IID process where the covariance is positive definite. W is positive definite. So if I had a regular sort of a quadratic cost function for this, that would be the linear quadratic Gaussian problem, LQG problem. But in the case of LEQG, so that's why the E appears here, you exponentiate the cost, quadratic cost, after you multiply it by some parameters, and this is the risk parameter is known as, and then you exponentiate it, and then take the expected value, and over the statistics of the initial state as well as the disturbance. And then you take the logarithm of this to bring it down to the same level, and then multiply it by 2 over beta. This is the inverse of this, and then 1 over t. You take the average, time average of this, and then let t go to infinity. So this is the performance. This is what one wants to minimize in the LEQG problem. And so what one can show is that this cost does not have necessarily a finite value, but it has a finite value provided that beta is smaller than some threshold, beta star. And that beta star depends on the problem parameters, the Q, R, A, and B, as well as W. And so if beta is less than beta star, it's not only that it's finite, but the minimum exists. And there exists a unique optimal control, and this unique optimal control is linear in the state. And this beta is related to the gamma that as I will introduce shortly, the gamma that I had in the H infinity bound. And there's a relationship between the two. I'll make that clear shortly. But the important thing here is that if you restrict yourself to linear feedback policies, you are not losing any generality. And so therefore we can take U to be minus Kx as we had in the linear quadratic regulator problem. So one can actually show that. So this is I was saying, what is the feasible set so that you have a finite value for this? If I replace U by minus Kx, which we know is no loss of generality, and if the Q here is taken as C transpose C in the mixed H2H infinity problem, and the W is taken as DD transpose, then the feasible set of this coincides with the one that I had earlier. This is the stability condition. And this one is an H infinity constraint, has to be less than 1 over square root of beta. So therefore the relationship between gamma and beta in this case is that beta is equal to 1 over gamma squared, or gamma itself is 1 over square root of beta. And so as I indicated, for this optimization problem, now you can formulate it as one of optimizing with respect to K. So this is a natural parameterization, and we're not losing anything by this parameterization. And you can, one can introduce what's called a generalized algebraic Riccati equation associated with this. Note that I should note that if beta is equal to 0, both here and here, and then pk tilde is just pk, and so therefore you replace this by pk. This is a Lyapunov equation. But with exponentiated cos, you no longer have a Lyapunov equation. You have a Riccati equation, and which is what we call a generalized algebraic Riccati equation. So the question is, what is the is there a closed form expression for this cos, assuming that it's finite, and what are the conditions under which that holds? And so this lemma, which is in that archive paper proven there, shows that it is the form of the cos function for the linear exponential Gaussian problem is precisely the one that I had earlier for the mixed H2H infinity problem. And this holds under two conditions. First of all, you need stability. And stability in this case is not just the stability of A minus BK transpose. Because of the exponential form, there is also this term coming in, and beta is coming in. And again, the beta cannot be too large. And essentially, if beta is very large, it means that this is a with sensitivity. I mean, there is a sort of a beautiful interpretation of this, what role the beta plays. It is the degree of pessimism that an individual has in coming up with a decision rule over an infinite horizon. And there is a finite horizon version of that as well. And so if beta is too large, then it means that the degree of pessimism is very high, and so therefore there isn't much to optimize in that case. So there has to be some threshold on the degree of pessimism of the individual. And this is all related to also the, you can come up with an adversarial interpretation of this with a risk-neutral control. And you cannot have a disturbance and driving your system which has too much flexibility. And that's what the H infinity norm actually stands for. So, so you have this condition, and as well as this condition. Of course, this one ensures that you have an inverse here, well-defined inverse. But the important thing here is that in addition to these two conditions is this. And so therefore, what one has to do is you want to minimize this. If I want to solve the LEQR problem using reinforcement learning techniques, I have to minimize this over K subject to these two constraints. And this also covers the maximum entropy H infinity control problems, as well as the linear quadratic zero-sum dynamic games. And I alluded to this. For the zero-sum dynamic game, what you have is now you have a cost which is not exponentiated, but this is actually equivalent to the exponentiated one, but without the disturbance. So here you have, this is a soft constraint on the disturbance that enters into the system. This is a disturbance which is not under the control of the controller. And so therefore you can view this as a game between the controller and the disturbance wants to maximize and the controller wants to minimize. So there's a strong connection to LEQG of this. Here, of course, since this is a game, you are looking for a saddle point equilibrium or Nash equilibrium, but for zero-sum games, it's saddle point equilibrium. And if you pick beta, if you pick gamma, 1 over gamma squared to be equal to beta, or beta equals to gamma, 1 over gamma squared in the LEQG problem, then you have the optimal control of that problem is the best control in the zero-sum game as well. But note that here you have a separate maximizer, and so therefore you cannot just formulate this as a single agent minimization problem. There are multiple agents here. So you have a multi-agent problem, but the end result, even though the process itself of using reinforcement learning on that problem will have to be a totally different one, and that's ongoing research, you do have the end results, that's the optimal controls, that's the solution for you, will have to be the same by the theory. And again, as gamma goes to infinity, note that if gamma goes to infinity here, you are putting a lot of weight on the disturbance, and in fact an infinite weight, and then this is just a linear quadratic regulator problem, and the only condition you have is the stability condition in that case. So let me now talk about some algorithms, which is the main part. I had a long sort of a description of the problem. I wanted to make sure that you all would have a good understanding of what problem we are addressing here. And now the question is, what sort of algorithms can we develop a policy optimization algorithm to solve this problem when we have this additional H infinity constraint? So again, this is the problem, as I indicated, and there are different equivalent forms of JK, but this is one form, which is the form that we had in the LEQG problem as well. And in this case, the PK solves this and this one. So the interesting thing here is that this constraint is, this is a frequency domain constraint. And this way it's possible to turn it into an algebraic constraint, which is very useful in the analysis and the development of algorithms. Now, what's the optimization landscape like? I mentioned this just briefly when I was discussing the outline. So the linear quadratic regulator problem, where you have no robustness concerns, when you iterate, when you use a descent-based algorithm, and if you decrease the cost using an appropriate step size, then you are assured that you do not go outside the stability region. Okay, so this is the stability region, let's say, and then you are decreasing the cost. So these are constant cost curves as you, these are actually decreasing in value. And if you go from K to K prime to a lower cost, then you are assured of staying in the stability region. This, however, is not the case with the H2 H infinity control. Decrease of cost does not necessarily mean that you stay within the constraint set. And in particular, it's quite possible that you could violate the H infinity norm constraint, that is the robustness, during the learning process. So this is one important aspect of the mixed H2 H infinity design, which you do not see in the LQR design. And so here this lemma summarizes this. The H2 H infinity mixed design problem over K is non-convex, first of all, and the LQR is also non-convex, but it is non-coercive, whereas the LQR is coercive. That is, as K goes to the boundary of delta K, then the JK does not necessarily approach to infinity, which is the case in the LQR problem. So that creates a difficulty. Now, how can we then enforce this, that at every step of the iteration, if you start within the constraint set, you stay within the constraint set during the learning process. In other words, you don't lose robustness. So there are three policy gradient algorithms, and one is the standard policy gradient. You take the gradient of J. By the way, the J is continuously differentiable in K for the problem at N. And you take the gradient J, and then the eta is the step size. And then this takes you to another point. And the gradient of J, I have written down here what it stands for. The natural policy gradient is one where the difference here is that you have multiplied this by lambda K inverse, where lambda is defined this way. And then you have the Gauss-Newton one, which is also well known to this community, where this is the iteration. Now, the natural policy gradient is essentially the policy gradient over a Riemannian manifold, and it's further discussed in this paper. And the Gauss-Newton algorithm is when you pick eta equals to 1/2, and we'll encounter this also shortly. It reduces policy iteration for LQ games. So I want to talk about, which is again something that I had brought up, the implicit regularization property. Now, the regularization leads to, for the iterates, to be confined to K. That is, you want to stay robustly stable. And one way of doing this, of course, in general, if you want to stay in the constraint set, you want to do a projection onto K. But script K is a non-convex set, so that's not ideal. And it turns out that, and this is something we show in the archive preprint that the natural policy gradient and the Gauss-Newton methods, they implicitly regularize the iterates. In other words, you don't need to do any projection. And so therefore the robust stability is automatically preserved as long as you stay in the, as long as you start in the constraints. So what are the, of course, it depends on the step size that you take and how small or how large the step size should be. And here are the two. As I indicated, it's for the natural PG and the Gauss-Newton that this holds, this implicit regularization. For Gauss-Newton, you need eta to be less than or equal to 1/2. And for natural policy gradient, you need eta to be less than this quantity, where this is the initial value, depends on the initial value of K0. And then if you start with, or if you are in the constraint set, then the next iterate also is in the constraints. Okay, so this theorem is proven in the paper. And so the proof, let me just very briefly talk about the proof. There is a very useful result called bounded real lemma, which is used in the proof extensively. This allows frequency domain constraint, which is what an H infinity norm constraint is, to be replaced by algebraic conditions. Specifically, what bounded real lemma says is that these three conditions are equivalent. The first one is that the control gain K lies in script K. That involves a frequency domain constraint. The second one is the generalized algebraic Riccati equation that we had in the case of the explanation LEQG problem. It admits a unique stabilizing solution such that this is satisfied and this condition is also satisfied. And that is, you have this stability condition and this is a positive definiteness condition. And note that the PK in this case is involves a solution of a Riccati equation, or the algebraic Riccati equation, or what we call generalized algebraic Riccati equation. And then the third condition, which is equivalent to these two, is that there exists some P such that this condition holds, and there is this Riccati inequality, so strict inequality here, where P tilde here is defined in terms of this. So this is the, again, a Riccati equation because of the presence of this term. So these two are actually used, these two conditions in the proof, and the equivalence of these conditions, and the fact that is also, they're also equivalent to the first one. So we use the linear matrix inequalities, that it's an LMI-based proof technique. Bounded real lemma, which I had on the previous slide, is used. And that is connected to the Riccati equation, and from there we go through perturbation to a strict Riccati inequality. And we construct a solution to the non-strict Riccati inequality, and plus a perturbation of some Riccati equations that leads to a strict Riccati inequality. So the details are found in the archive paper. So what's the global convergence now of this? Now that we know that if you start with those two algorithms, the Gauss-Newton and natural PG, if those two conditions are satisfied, then you remain in the set, in the constraint set, if you start in the constraint set. So the question is, does that ensure that we converge to a global optimum? And this theorem says that yes. The step size choices that I had for these two, the Gauss-Newton as well as the natural PG on an earlier slide. If you use those step sizes, then we can prove that we have convergence to global optimum, and it is at a sublinear rate globally. The controllability assumption is not, it's a fairly reasonable one. And in fact, it's satisfied automatically for the LEQG problem, because in that case, the D is the square root of the W. And so it's full rank and in fact, positive definite. And it is not, we don't have the no global gradient domination as in LQR in this case, and only sublinear rate, convergence rate globally. Now, locally, we can show that the convergence is faster and it's super linear around the optimum. So let me discuss some simulation results before I conclude. So we have two sets of simulations here that I'm going to present. One is where we start initialize K, the iteration, fairly far from the boundary. And the underlying system is a three-dimensional system. The step sizes taken is for, we also include policy gradient here. This is 10 to the minus 4. For natural policy gradient, it is 5 times 10 to the minus 3. And for Gauss-Newton, we take it to be 0.1, as well as the 0.5. And as you'll recall, the step size constraint for Gauss-Newton was it had to be less than or equal to 1/2. So this is the limit. And what you can see here, so in these figures, you have the average gradient norm square, its convergence, and the best is what you see here is the Gauss Newton when you pick the step size to be 0.5, the limit, and this one is here you can see the difference between the cost function at an arbitrary K, well, at the iterates, and then as compared to the optimum value of JK star. And here I should indicate that if you have difficulty in seeing, this is 10 to the minus 10. And this one shows to what extent we satisfy the H infinity norm. And this is the H infinity norm that we took for the simulation. And even this policy gradient, even the policy gradient meets this with this step size, does not violate during the learning process the H infinity constraint, that is the robustness constraint, gamma. And again, this is the Gauss-Newton, and with 1.2, and this is Gauss-Newton with 0.5, smaller step size, and these two are the policy gradient and the natural policy gradient. Now, the next set of simulations are those where we start near the boundary of the constraint set and take real infinitesimal step sizes for PG, because we know that it would not, even with infinitesimal step size, we are going to see that we are going to violate the constraint. And so the step sizes is 10 to the minus 8 for the PG, and 5 times 10 to the minus 4 MPG, and 0.1 for GN. And again, here, the only thing is, from here, you can actually see the sublinear convergence rates. And one thing that I should point out, that note that you start very close to, here you cannot tell, but you start very close to the H infinity bound, which is the robustness that we want to achieve. And the policy gradient actually violates this, because we are close to the boundary, violates this initially, and then it satisfies it. And all others, the other two do not violate the H infinity constraint throughout the learning process. So to conclude, I have just a couple of minutes. So what we have here is a better theoretical understanding of policy-based methods in learning for robust control and robust risk-sensitive reinforcement learning in general. We have seen the effectiveness of the H infinity norm constraints in making sure that we have strong robustness in these continuous control tasks for reinforcement learning. And we have a global convergence theory for policy gradient methods for mixed H to H infinity control synthesis, and as a special case for risk-sensitive optimal control and decision making. And again, I should emphasize that the difficulty here was the non-coerciveness of the constraint set, and we have shown implicit regularization for this class of problems, and for two of the methods, policy optimization methods. And so therefore the robust stability is preserved throughout the learning process. Now there are many possible extensions of this, and some of this is ongoing work. And I mentioned that there is equivalence between a linear exponential quadratic Gaussian problem, the minimization of exponentiated cost, and the linear quadratic zero-sum differential games, where the cost is not exponentiated, but that brings in one additional player into the picture. You don't have a single controller, so it's not a single agent problem, but a multi-agent problem. And that brings up questions of whether the updates, the learning process should be in parallel or should be in sequence, which leads to inner-outer loop updates. And there are some initial results on this. This is still ongoing work. And the sample complexity is another topic that falls squarely in this class of problems, in this framework. In this case, the naive zeroth order methods fail, and there is I discuss only linear systems, but mixed design possibilities exist for other types of dynamical systems. For example, you could have jump parameter systems, Markov jump parameter systems. You could have systems which are where you have state constraints, and how can those be handled within this framework? And the other one, which is a difficult problem, is how to minimize directly the H infinity norm of the of the transfer function. And that's a non-smooth optimization problem. The others were smooth optimization problems. Of course, from a theoretical point of view, if you are not looking at policy optimization, this the minimization of this norm is equivalent to solving a zero-sum game or solving a linear exponential Gaussian problem. And there, for the LEQG, you look for the largest possible value of data, and that corresponds to the minimum value of this H infinity norm. But how to come up with a policy optimization methods for this non-smooth optimization directly, that's a challenge. And at the higher level, how to enforce safety robustness constraints on the fly in policy-based, model-free reinforcement learning in general. And that's also an important future direction. So I'll stop here, thanking you for your attention, and let me know if there are any questions.
Okay, thank you, Professor Başar, for the great talk. And so as for the questions, it seems the first one is regarding whether it's possible to, so how to find the initial point in the algorithm. It seems that you need to find a point inside of the constraint.
Right. Well, we do have different ways of finding that, and the archive paper discusses it, and you have to come up with it's a sort of a trial and error, but it's a convergent method. It's something that quite easily leads to the to a feasible initial point. So there are different ways of approaching that. Let me maybe Kai-Ching may want to add. I'll bring in my two co-authors here if they want to add, because Kai-Ching did the simulations and he didn't have any difficulty in coming up with feasible initial conditions. But Kai-Ching, do you want to say anything?
Oh yeah, hi. Hi everyone, this is Kai-Ching. Thanks a lot for the organization and the invitation. So regarding that question, actually, first of all, I would like to note that in all these policy-based methods, even in the policy-based method for solving LQR, the initialization, the feasibility of the initialization is a very common and standard assumption. And so that's why I assume that. And then in order to achieve that, when we currently we are doing that is first of all, there are some methods, model-free methods to estimate the H infinity norm for a given controller. And then it's like a noisy, then we can easily get an estimate of the H infinity norm using data. So it's model-free. And then we can apply some zeroth order method. So meaning that we can get as long as we can get an estimate of this H infinity norm, and then we do kind of the zeroth order method. At least in the simulations, I can successfully decrease the H infinity norm so that it will be smaller than some gamma. There are some other methods. For example, you can estimate the model ABCD very coarsely. You can have very coarse estimate of the model, and then you can do a model-based approach to find such an initialization too. We have some discussions in the paper, so for those who are interested, you can check out the paper.
Oh, thank you, Kai-Ching, for the thorough explanation. So it seems there's a follow-up question regarding on the initialization problem. It says that in this setup, it still needs to it says in your setup, it still needs to guarantee a certainty H infinity norm in the initialization, which is different from the LQR step. It's different from the LQR setup. where any stabilizing controller is okay. So I guess, well, maybe it's asking whether finding the initialization is more challenging than the LQR setup.
Well, it is more challenging, but I think the Kai-Ching has answered that, that question, and the paper has some talks about ways of making sure that that's satisfied by the.
Yeah, it's I would say it's more challenging than finding a stabilizing controller, because for LQR you only need to find a stabilizing controller, and we all know that the stabilizing controller always admits a finite H-infinite norm, but it's not necessarily smaller than the gamma we require. Therefore, what we are looking for is a restrict, I would say, subset of the stabilizing controller. So therefore, in that sense, it's more challenging. I agree with that.
Yeah, I also want to say that like this.
One thing that I want to mention is that you cannot pick also gamma. I mean, there's an art in picking gamma as well. You cannot pick gamma too small, because then you cannot, the problem does not have a solution. Just like picking beta in the LEQG too large, then you don't have a solution to the problem. Sorry, Ben.
Okay, yeah, so I think I want to just clarify one point. It's like how to provably stabilize the system, or what's the sample complexity of stabilizing system, or what's the sample complexity of updating a controller satisfying certain infinite norm. This is still an open question, I would say. You know, so we do have some heuristics way to decrease the H-infinity norm. We also have some heuristic way to update a stabilizing initial controller, right? But for those, how to provably get those type of like initial points, I think like the theory has not been completely figured out.
Oh, thank you, Professor Hu, for the.
But the paper, I would say, the focus is more on if you do have a robust initial policy, how to maintain the robustness level, while you can further, of course, decreasing the cost. You know, so I think that's the focus of the paper. So it's not on improving your robustness. It's really about maintaining or preserving the robustness. That's the focus of the paper.
Thank you. So another question is regarding on whether it is possible to generalize the results to the output feedback case. Currently, it's assumed that the state is directly measurable. So I guess it's maybe asking whether it's possible to allow there's an observation channel.
Yes, I mean,
partially observable case.
In this with the other, we have some discussion of that, and that's definitely a future work. And so there are two ways of addressing that generalization. One is the output by output feedback. Do you just should it just be a static feedback? In other words, you have a parameter like k, and then I do multiply y, so the control u is minus k times y, where y is the measurement. That's one way, but that's not a good, if you have a measurement which is much lower dimensional than the state of the system, that's generally not a good way of approaching the problem, but that's definitely doable. The second one is to have an observer, or in the case of the linear exponential quadratic Gaussian problem, you can have, there is a theory for if you have noisy measurements, linear measurements, then there's a Kalman filter, there's some sort of a separation principle that holds, not quite as in the LQG problem. And then in that case, you have to optimize over not only the gain on the control, in the control which multiplies the Kalman state, estimated state, but also the Kalman gain itself will have to be optimized. So you have a highly nonlinear, highly non-convex optimization problem. but I'm not saying that it cannot be solved. I mean, it's a totally different sort of set of tools that will have to be brought to the table, and definitely we are interested in pursuing research in that direction as well. Kai-Ching, do you have anything you want to say?
Oh yeah, that's pretty much what I wanted to say. But one thing to note is that even for LQR, the output feedback using policy-based method, the global convergence hasn't been, to my knowledge, hasn't been well studied. Because even in the, like say, the output feedback case, you may not have global convergence anymore, because the matrix C times before the state may not be full rank in that sense. So the global convergence, you can only, I think there is one paper by Polyak very recently. They show that you can converge to a stationary point in that output feedback case for LQR, for LQ case, not a robust case. But I think that's still an active research area.
Okay.
Even for LQR, non-robust one.
Yeah, so the Polyak's paper is about static output feedback. So it's like you have a static just matrix, not a dynamic controller. So he shows in that case, you can show a global convergence to a stationary point at a certain sublinear rate. And then if you have a dynamic controller, that's still open problem. And then for our case, I would say possibly the static output feedback problem, we may get similar results, but the general like dynamic controller case, what's the optimization landscape and how policy optimization works there is really interesting but open question right now.
Okay, thank you. Maybe is it possible that you elaborate more on the explaining what's the difference between a static and dynamic controller?
So the static case is okay, Tamer, you can go.
Yeah, I mean, just consider the LQG problem, the standard LQG problem. You can, and you have a noisy channel, and you don't have perfect access to the state. So if the state is X and the measurement is Y, you don't have minus K times X, but you can do minus K times Y, where Y is generally much lower dimensional than the state itself. So that's what I would call static output feedback. Now, we know that is not optimal even in the case of LQG, because in LQG, then you have to bring in Kalman filtering. You have to generate an estimate of the state, and then you apply your control gain, K, multiplies by X hat, where X hat is the estimate of the state. And the X hat is generated by a filtering equation, which is of the same dimension as that of the state itself. And that filtering equation is, it's another dynamical system, which has as its input the measurement itself. And it is, there is also the Kalman gain itself in that case is given from the solution of an Riccati equation. So that's a dynamic feedback. So the difference is that in the case of static, it's just you have one matrix that you will be optimizing over. In the case of a dynamic feedback, especially if you want to obtain the real optimum solution, you have two matrices. One is again the control gain, and the other one is the Kalman gain in the filtering equation. And the Kalman gain is of dimension state times the dimension of the measurement. And so that's, and then you have a very sort of complex, it's not that you cannot write down the cost function, but you have two sets of parameters, and these two sets of parameters enter in a highly nonlinear way because you have these product terms as well.
Okay, thank you. And the next question is that it seems that you have shown in one slide that the LEQR problem, linear quadratic exponential Gaussian, is equivalent to the H2 infinity mixed design. That means, in some sense, for the LQ system, risk sensitivity is somehow equivalent to adversarial robustness. I was wondering whether such equivalence holds in a broader context for other models.
Yes, one can show that actually for nonlinear systems as well, such an equivalence holds. In other words, of course, to be able to talk about H infinity norm, you're dealing with transfer functions, so you need linear systems. But if I want to look into the connection between exponentiated cost, minimization of an exponentiated cost for maybe a non-quadratic cost function, mm-hmm. and for a nonlinear system, is there an equivalent game, zero-sum game, so that the solutions for the optimum solution for the exponentiated cost problem, that this is a single agent optimization problem, provides the best controller for the zero-sum game, and vice versa. And yes, there is such an equivalence. And in fact, if you are dealing with nonlinear problems, then you have to look into for the optimal control problem or the linear exponential Gaussian problem, you have a dynamic Hamilton-Jacobi-Bellman equation that the value function satisfies. And that Hamilton-Jacobi-Bellman equation is exactly the same as the Isaac's equation in the case of the zero-sum game with nonlinear dynamics and non-quadratic cost functions. Mm-hmm. Okay. So this is discussed in several. I mean, I can send papers, but also it's also discussed in the book I have with Pierre Bernard when we look at the equivalence between these two, even for nonlinear problems.
Mm-hmm. So it's the H infinity robust control book, right?
Well, in that case, you cannot talk about H infinity robust control. You talk about the operator mapping from the output, from the input to the output for a nonlinear system. And you want to minimize the L2 norm of that over all possible inputs. Mm-hmm. So you no longer have a frequency domain interpretation, but you have a time domain interpretation in the using operators.
Mm-hmm. Thank you. Maybe we have time for the last question. It's let me see. So the question is as follows. It says that is it possible to directly minimize the H2 norm like in the LQR case? It seems that in the presentation, JK that is defined in the slide is an upper bound on the H2 norm.
Well, it's an upper bound because of the additional constraint that needs to be satisfied, and that is built into that upper bound. And so normally you would not obtain the H2 minimum if you have a constraint, H infinity constraint, because that further restricts the class of all available controllers. So Kai-Ching, do you want to say anything on that?
Yeah, actually, I think that's a very nice question. If you think about it, the H2 H infinity, people may think of directly minimize the H2 norm and subject to H infinity constraint. But the thing that following, first of all, the formulation in our paper follows the standard formulation in the control literature. People call it H2 H infinity mixed design. Another thing is that using this formulation, we can have a very nice equivalence between the risk-sensitive control, the linear quadratic games, and also the maximum entropy H infinity control. So I'm not sure in the directly minimizing case whether this equivalence still holds. And also I haven't seen, at least to my knowledge, I haven't seen actual this kind of formulation in the literature. But I would say in that case, the landscape would be very different. And if there exists such a formulation, it's still worth investigating.
Yeah. So for that formulation, you know, people usually, like when they do model-based approach, they will use non-convex formulation. So typically, they use something called a bilinear matrix inequality, which is non-convex, and they can use like a path-following algorithm. So for those problems, even the existing model-based approach cannot be guaranteed to solve it globally. So it can only give you local solutions. And so I would imagine like for like policy optimization, if we apply policy optimization for those type of problem, we will also not be able to get global convergence guarantees, but it's possible you may get some local convergence guarantees. But whether you do still have this implicit regularization property is not known at this moment, and like whether you can achieve like a reasonable rate is also not known. I think that's a very interesting open problem right now.
Mm-hmm. Thank you. It seems I'm running out of all the questions. And yeah, maybe let's just stop here. And thank you, Professor Başar, again for the great talk. And also thank you, Kai-Ching and Professor Hu, for answering the questions. And
thank you so much.
Yes,
thanks so much.
Thank you. And also thanks everyone for joining today.
Thanks for organizing this.
Thank you. Thank you, Professor Başar. And also thanks everyone for joining. And we are looking forward to seeing you guys next week. Thank you.